So welcome to part 3 of lecture 34. We're going to kind of look at a different operator. In the last part we were looking at positive operators. In this part we're going to look at an isometry. Okay, so an operator is an isometry if when you take the norm of your vector and you compute it and you evaluate v at that operator and you compute its norm, you get the same value. And this is true for all vectors in your vector space. So we're saying here that one way to say what we're doing here is that norms are preserved by S. Okay. Now again, let me try to tie this back into math 1B03 or 2LA3. Recall that we say that a collection of vectors in Rn is an orthonormal set, right? If each of the pair of vectors, distinct vectors, are orthogonal, and the length of each vector, because if we're dealing with Rn, we can talk about the length or the norm is 1 for all I. And an n by n matrix U, whose columns are an orthonormal set, is called an orthogonal matrix. Now, to be honest, I think this is kind of a poor choice of definition because you would expect an orthogonal matrix to have columns whose columns are orthogonal, but we're actually imposing an extra condition that each of the columns form an orthonormal set. And U then has the property that when you take U and you multiply it by a vector X and you compute the norm, you get the same norm of the original X, right, for all X inside of Rn. So this is actually the property that we are going to try to generalize. So we want to generalize that. So if you want to think of something kind of concrete when we're talking about an isometry, think of a matrix whose columns are an orthonormal set. Okay, and like the positive operators, there's kind of a characterization of when an operator is an isometry. So there's a whole bunch of things here that are kind of very useful. So S is an isometry. When you take the inner product of S, taking two vectors u and v, evaluating them at S and computing their inner product, it's the same thing as taking the inner product of u and v. So what this is saying is that the inner product is preserved, okay, between these two vectors. The next one is that if E1 through En is orthonormal, then after you evaluate each of those vectors at S, then the new set is also normal, or it's also orthonormal. Okay. The next thing is that if there's an orthonormal basis of V such that SE1 up to SEN is orthonormal. Okay, and this part's not too, it follows kind of directly from the previous result because if V is an inner product space, you can use Graham-Schmidt to make an orthonormal basis, and then you can just apply the part C to prove part D. The next property about isometries is that S, taking the adjoint and composing it with S gives you the identity operator, and same thing with the reverse direction. If you take S and then compose it with S, its adjoint, you get the identity operator. You also get that the adjoint is an isometry. And finally, you get that S is invertible, and the inverse of S is its adjoint. And we actually proved kind of a special case of this when we were looking at orthogonal matrices in the last lecture. I kind of went through this, but if you don't see the connection, that's fine. Okay. Okay, so I'm not going to prove everything, but I feel like I should prove something in today's lecture. I haven't really proved anything yet. And so I'm going to prove that A and B are equivalent statements, okay? And you actually need a trick depending upon which field you're working with, okay? So if you're working with the real numbers, you need the fact that the inner product of A and B, you can write everything in terms of norms. So it's the same thing as the norm of A plus B squared minus the norm of A minus B squared divided by 4. And if you're working in the complex numbers, the inner product of A and B can be expressed in terms of norms. Okay, so inner product expressed in terms of norms. Okay, so the book does R. Okay, and I will do the case that F is the complex numbers. Okay, but I will do that case as part of the last part of lecture 34. So I'll pause here and I'll see you after the break.